Acid-catalyzed hydration and oxymercuration-demercuration are used to add water to alkenes in a Markovnikov sense, with the OH group ending up linked to the more substituted carbon in the product so that we get the more substituted alcohol. But what if we want the less substituted alcohol? This would be associated with the so-called anti-Markovnikov product, and the way we do this is using a reaction called hydroboration-oxidation, and that's the subject of this video. Fundamentally, hydroboration-oxidation is different from acid-catalyzed hydration in that the hydrogen source in this reaction is not electrophilic, but nucleophilic. In acid-catalyzed hydration, we make use of something like H3O plus or H2SO4, something with an electrophilic hydrogen atom, a hydrogen atom with partial positive charge. In hydroboration oxidation, we make use of a borane, BH3 or some other boron-containing compound with a BH bond, and that H in the BH bond is actually nucleophilic rather than electrophilic. And to provide evidence of this, I ran some calculations on BH3 and wanted to point out that if you look at the partial charges on the hydrogen atoms in this molecule, they're partially negative, indicating that these hydrogen atoms are nucleophilic rather than electrophilic. This fundamentally changes how they add to the alkene. Since the hydrogen is the nucleophilic bit in BH3, just like the nucleophile adds to the more substituted position in acid-catalyzed hydration and hydrohalogenations, the nucleophilic hydrogen in this reaction is going to add to the more substituted position. This is ultimately going to lead to anti-Markovnikov hydration after we replace this boron group with an OH, which is done in the second step. So the reaction is a two-stage process. First, we use a borane, such as BH3THF. We'll come back to that in a second. And then we convert the boron group into an OH using basic oxidation conditions. So something like sodium hydroxide and hydrogen peroxide is probably the simplest way to go about doing this. Now, let me talk a little bit about this reagent BH3THF. So BH3 on its own is a pretty reactive Lewis acid. It's so Lewis acidic it will actually bind to itself and form a dimer B2H6. We see that here. So typically when BH3 is used as a reagent, it's complex to some Lewis base. And the two most common are tetrahydrofuran, which is this molecule here, and dimethyl sulfide, which you'll see abbreviated as Me2S or DMS at times. So this BH3THF reagent is really just a source of BH3. THF dissociates reversibly from the complex, and BH3 ends up present in small concentration, but large enough concentration to add to the alkene. So notice that the overall reaction here is an anti-Markovnikov hydration. Hydrogen is added at the more substituted position in the initial alkene, and OH at the less substituted position. To begin exploring why this anti-Markovnikov addition comes about, let's take a look at partial charges in the alkene. Something we've noted about alkenes is that the more substituted carbon is better at supporting positive charge. If we ended up with a carbocation right here, it would be more stable at that more substituted position. This leads to a situation in the starting alkene where there's more partial negative charge on the less substituted position and less negative charge or more positive charge, depending on how we want to think about it, on the more substituted position. So this position sort of goes with the nucleophilic hydrogen in BH3. This is why this hydrogen ends up linked to the more substituted position, and boron, which is more metallic, more Lewis acidic, ends up linked to the less substituted position in the alkene. Insight into the mechanism of hydroboration is provided by the stereochemistry. If we use a substrate that would give different products on syn and anti-addition of H and OH, we see that hydroboration is stereospecific. The hydroxyl group and hydrogen add in a syn manner to the same side of the alkene. So for example, in this particular case with this methyl cyclohexene, we get two products that are enantiomers of each other, but both of them have the same relative configuration with respect to the H and OH. H and OH are on the same side of the cyclohexane ring in the product. This corresponds to syn addition, H and OH adding to the same side of the original alkene. And this can be explained by the mechanism, as we'll see here shortly. So a mechanism consistent with the regioselectivity, anti-Markovnikov, and this syn stereospecificity involves a first step where bond formation between carbon and hydrogen and carbon and bromine is concerted. So both bonds are forming at the same time via electron flow from the BH bond to the alkene and from the alkene to the boron. So that's going to look something like this. We're going to draw an arrow from the BH bond to the more substituted position. I like to do this to show the hydrogen, nucleophilic hydrogen bonding to the more substituted position of the alkene, and an arrow from the alkene back to the boron, showing bond formation between the less substituted carbon and the Lewis acidic boron. This produces an alkyl borane, and we've added the hydrogen. All that remains is to add the OH group, and this is done in the oxidation stage, which converts this BH2 group into an OH group with retention of configuration. So if a stereocenter was set at this carbon linked to the boron, that configuration is going to be retained in the oxidation step. Relatively simple. We don't need to think or worry about inversion of configuration or any stereochemical change at that carbon in the oxidation stage. This mechanism, going from the alkyl borane to the final alcohol product, is a little more complicated, and we'll dig into that on the next slide. One thing I want to back up and mention is that because the starting alkene is achiral in this case, and the reagents are achiral, we would expect a racemic mixture, equal mixture of the two enantiomers in this reaction, and this is typical of hydroborations of achiral alkenes. Generally speaking, you don't need to worry too much about the oxidation stage of hydroboration oxidation, as long as you keep in mind that this reaction occurs with retention of configuration. The boron group is simply replaced with an OH group. But in case you do need to know something about it, here is one idea for how the mechanism works. So the second stage involves combination of a hydroxide salt, typically sodium hydroxide, with hydrogen peroxide. This generates small amounts of the hydroperoxide anion, which is a nucleophile, and adds to boron, which is a great Lewis acid, great electrophile, and we end up with this complex, and I'm realizing now this should be negatively charged, right? Essentially the negative charge, at least formally, has been transferred from oxygen to boron. This boronate anion can undergo kind of an interesting rearrangement step with loss of hydroxide, something like a 1-2 rearrangement with SN2 displacement of hydroxide at this oxygen. It's a funky looking step, but it kicks off hydroxide and generates this new borane with an OR group where there was an R group before. So essentially we've accomplished the oxidation, right? We've made the OR bond, the O carbon bond, and all that remains now is to replace this fragment with a hydrogen. These same couple of steps can happen multiple times, replacing all three R groups with OR groups, and we end up with this. And then we get an addition of hydroxide, which was generated in all of these rearrangement and displacement steps, and that generates this anion, which can lose an OR minus, loss of a leaving group step, that can get protonated, and there's our final alcohol. So really the key to this entire mechanism is this rearrangement and SN2 displacement occurring in a single step. This is what establishes the carbon-oxygen bond. The rest is mostly proton transfers or nucleophilic attack of these anions, OH minus and the hydroperoxide anion at boron. In this practice problem, we're asked to predict the major diastereomer product when alpha-pinene, which is this alkene right here, is subjected to hydroboration oxidation conditions. And here we're going to assume that hydroboration occurs on the less sterically hindered face of the alkene. So this alkene has two different environments going on. It's got this bridge on one side with the two methyl groups and this bridge on the other side with two hydrogens. So we can end up with diastereomers in hydroboration oxidation, and we'll talk through the steric hindrance issue here in a second. Let's start with the basics, keeping in mind, based on how hydroboration oxidation works, where the H and OH end up. So hydroboration oxidation is an anti-Markovnikov method, and so OH will end up at the less substituted carbon and H at the more substituted carbon, but this will happen with syn stereospecificity. So H and OH will approach the same side of the alkene, but they could approach from above or from below, and in this case, this will lead to diastereomers. Again, one way to see this is to notice the two different bridges on the two sides of the alkene. One diastereomer involves H and OH coming from above. That would lead to this product, and we can see the H and OH there. The other diastereomer would involve H and OH coming from below and would look like this. And these are indeed diastereomers since they differ in configuration at these new stereocenters but have the same configurations at these stereocenters that were not involved in the reaction. All right, so there are H's and OH's, and in thinking through which diastereomer will be favored, we want to consider the two different steric environments above and below the alkene. And what we can notice is that these two methyl groups above the alkene create steric hindrance, create some blockage of that face or that side of the alkene, making it harder for the borane reagent, for example, to access the alkene from that top face. This also creates potential steric issues, steric clashing, steric strain in the product of approach from that top face. And so approach from the bottom face here is likely to be favored, and the major diastereomer is going to be this one with the OH group and the new hydrogen underneath the alkene, bonded to the more open face of the original alkene.